Oh, well, good evening, everyone. We are working on section 11.9. That's kind of where I am right now. And okay, got somebody just turned up to distract me. Three main ideas, concepts that you'll find in 11.9. After this, hopefully we'll get on to 11.10. It depends on how smoothly we go through these. And when we get to the next section, we're going to look at how to create from scratch Maclaurins, which are power series centered at 0 of a function, and how to do Taylor series, which are power series centered at some other number like x equals a. So we've done quite a lot of practice at this, and I'm going to do just one more, just as an overlap, where we're going to use these two standard power series to create the power series for a rational function. So, it was mostly substitution, right? And good stuff like that. And after that, we're then going to look at a trick that you can use to generate power series of even more functions. And what we essentially are going to do is we're going to find the power series of a function, probably a fraction. And then if you differentiate it, you'll then be able to create a power series of that new derivative. You can see that very clearly. But essentially, you have a power series, you'll differentiate the left and you'll differentiate the right. And the function on the left has the power series on the right. So it's a kind of trick you can use. And that will allow us to find things like what? Like power series to the natural log of 1 plus x or something, whatever. That's a good one, I think. And same idea, but now we're going to integrate a power series to find the power series of another function. And although I've not written it down here, I'm also going to give you a list of essentially the most common functions and their power series that you deal with. And they're pretty extensive list, I would say. So let's look at this one here. How do you use either this or that to find the power series of a rational function? And the guy I'm going to pick is question 5. So we have a function that we're being asked to create a power series for. It's x squared over x to the 4 plus 81. And as it stands right now, it really isn't going to be possible to use either of these. Now, since I see a power of x and a number being added, I know it's going to be this guy. My big issue is this 81 is no good, right? That 81 is not going to work. Just can't use it. I also have that x squared, so I'm going to bring out that x squared as well. I'm going to do a 1. And I'm going to bring out 81, and that's going to get me x to the 4 over 81 plus 1. And only reason I'm writing this line down is that it looks prettier to me. So with a little bit of algebra, I've rewritten this in a slightly clunky form, but this form allows me to use this power series. Now, I know it has a power plus 1, but that's the same thing as 1 plus the power, so we can get away with that. So I can now replace this with the power series. And I'm using this guy, and it's going to be from n equals 0 to infinity. This x here and here, is going to get replaced by that package there. So essentially, I'm going to do x to the 4 over 81 to the n. Are you comfortable about this guy being converted into that power series? I'm essentially using this kind of building block 1, and I'm substituting the x for x to the 4 over 81. So far, so good. Right, now the next few lines are all about making it look pretty, right? Just style points. X to the 4 over 81 raised to the power of n can be written as 4n over 81 to the n. You comfortable with that? Then I'm bringing these two guys inside. And x squared plus this guy just adds an extra 2 to the power of x. And 81 added to this guy gets you an extra plus 1. And we now have our power series. That guy. And they finish with find the interval of convergence. So that's going to be the ratio test and the thing you've done about 20 of now. So I'm not going to do that part. But, you know, find the interval of convergence. You'll find R as well for free, and then test the endpoints. And you'll find the interval of convergence and the ratio R by using the ratio test. So hopefully we've done enough of number 1. Now, the next guy I'm going to do, there's only 2 of them, question 7 and 8. I'm going to do a version of question 7. And they give you, this is your goal. To find the power series of that function. He does not look like that guy. And algebraically, I won't be able to make him look like that guy. So we have to figure out how that's, how we're going to create a power series of that. So what you gotta do, I'm going to have to call it g of x, so it's not the same name as that is. You have to find a function that looks like this guy. At least when you differentiate it, it looks like this guy. So the function I'm going to pick is that fella. Now, just to check it out, if I differentiate this guy, you multiply by the power, and you reduce the power by 1. And technically, you differentiate the inside function, but since it's 1, it doesn't matter. I get that. So far, so good. Now, I look at this guy, and I say, darn it, I almost got it. I wanted this to come out, but I got that. So I may have to go back to this and tweak it a little bit. What could I add to this so that when I go through the differentiation process, I get positive 1 over 9 plus x squared?
Make it negative.
Right? And if you make that negative, you make that negative, which makes this positive, which makes this positive. So we have now found the go-to function. I am going to find the power series for this guy.
Are you okay? Yo.
Oops.
No.
I will fix
Bro.
that. There we go. You got to remember that I can hear you when you come. So bear that in mind. So where are we? Yeah. God, I'm easily distracted. So we now have a starting function. So what I'm going to do is I'm going to find the power series of this. And then I'm going to differentiate it. And when I differentiate this power series, that means I've now found the power series of the guy I want. So you see, it's a kind of sneaky trick. I can't find the power series directly, but I can find the power series of a function that once I differentiate it is the guy I want. So let's now focus on the power series for this guy. Well, I kind of need to do a little bit of a tweak. I'm going to pull out 9 and get that. Are you comfortable with, you have to have a 1 here. And I'm going to call it 1/9, 1 over 1 plus x to the 9th. Just emphasizing that, sucking out the stuff that I'm not interested in so that I can now focus on this piece. Now it's going to be 1/9. And if you do the 1 plus 1, shooting space. Does anybody know what I just did there?
An intentional mistake.
Ah, well done. No, an unintentional mistake, but if I can bluff it, I will. Does anybody know what's wrong with these two guys?
They're backwards.
They're
They should be
backwards.
switched.
Yeah. Now, the easiest way to fix it is make that a plus and make that a minus. And to make this question a negative. No, I can make this a plus. We're okay. I can leave that. So when I do the 1 plus x, it's going to be this guy, right? Okay. So it's going to be sigma n equals 0 to infinity, -1 to the n, this guy to the nth power. So it's -1/9, n equals 0 to the infinity, this guy, x to the 9n, 9 to the n. Now I'm going to bring in all of this inside the sigma, and we should be done. Well, there's not an awful lot happening. The 9 on the bottom can join that, and that gets me 1 extra power of 9. And there's nothing really happening with the x to the n, and I'm going to call that -1. So it joins this guy. You get -1 to the n plus 1. And that fella is the power series of this fella. So I now have kind of halfway there. Now, I'm going to differentiate this guy. So here we go. Negative that guy is equal to this power series. If I differentiate that function, don't we get that guy? Remember, if you differentiate it. So from here to here, I've differentiated. Now, you can differentiate power series. Isn't a power series just a very big polynomial? So shouldn't I just be able to apply the power rule? So multiply by the power and reduce the power by 1. Are you comfortable with, if you differentiate any one of these terms, don't you basically multiply by the power and then reduce the power by 1? And isn't everything else just a number? So everything else stays put. Looking good? Now, this power series is correct, but it's not in its style point form. It can be made a little bit prettier. And I don't know if WebAssign is pernickety or not, but I am. So this is how you fix it. We try, if it's at all possible, because sometimes it's not, to make this x to the power of n. Just looks better. Now, you notice that if you plug 0 into this expression, don't you get -1 to the power of 1 times 0 times x to the -1 all over that? And in other words, doesn't that basically disappear? Right? When n equals 0, that term is nothing. That means that I can do this little cosmetic movement. I have essentially just ignored n equals 0. And I can do that because if n equals 0, the answer is 0, doesn't have no effect on the answer, so I don't need to use it. Then I do this. This is the last line. I change that to x to the n. Now, I can't just change things without altering everything in the proper way algebraically. So I think of this n minus 1 becoming an n. Then I essentially add 1 to it. So every time you see an n, you add 1 to it. So far, so good. Now, this bit you might not like. You might think, oh, well, I think I got it. Every time you see an n, add 1. Every time you see an n, add 1. Every time you see an n, add 1. But not this guy. Now, let me try and explain why that starts at 0 now when you've done this transformation. If you plug n equals 1 in here and calculate what all the terms are equal to, in particular, doesn't that get you x to the 0? So if I plug n equals 0 in here, would you agree that you get some numbers and you get x equals 0? So this moving this guy from 1 to 0 basically realigns the sigma so everything is matching. So the formula part, which I mean this bit, add 1 to everybody. But the sigma part, reduce it by 1. And we now have the power series for that. So I think you just have to remember this probably. So this guy becomes 1 less, and these guys all become 1 more. Okay, so the function becomes 1 more, and the n on the sigma becomes 1 less. And that's going to be a truism. In other words, that's what you do when you're trying to rearrange a sigma to match the change that you've done. Are we good? There's only 2 examples of that, so I'm not going to steal the thunder and do the second one, so good luck. So now let's look at using integration to do a similar type of job. I'm going to take a little bit of time on these ones because they are pretty messy. This is the function I want to find the power series for. Is there any function you can think of that when you integrate it will give you that guy? Well, suppose it was just log n, right? If it was just log n, wouldn't it be 1 over x? And if it was 9 plus x, or in this case 9 minus x, you would get that, right? This doesn't quite match. It's almost correct, but do you notice that you're going to get a little negative caused by this? So if you put a negative here, you now get that. So let's check this out. If you integrate this, is the answer that guy, right? So if you integrate this, do you get that? Well, the rule would be -1 times the natural log times another -1. The 2 negatives 1 cancel, bingo. Would you agree it works? If you're wondering where does that come from, it comes from, you know, this bit here, right? It's essentially a chain rule. That means, oh, by the way, plus c, it's an arbitrary constant. That means I need to find the power series of that guy. I don't know if it's coincidence or not, but isn't it almost the same one as find the power series of this guy, right? So it's going to be very simple. So I'm going to take it and call it be comfortable with that. Pull out a 9, 1 minus 1/9 x. That's going to be 1/9 sigma. Now I can use the 1 minus x guy, which is this fella. So it's going to be n equals 0 to infinity, 1/9 x to the n. X to the n, 9 to the n. All you get is a single -1 here. Nothing happens to that guy, and this guy gets 1 extra power. We have now got the power series for this fraction. Is there anything you're not sure about where bits came from here? Is it looking good? So if I integrate this function, won't I get the natural log of 9 minus x plus some arbitrary constant c? So I am now going to integrate this guy. And so whatever this comes to as a power series will basically be the guy I'm looking for, right? So I can take this integration inside and integrate each one of these guys separately. Well, it's add 1 to the power and divide by the new power. And that 9 to the n plus 1 is just a number, so it stays put. Plus c. And so the natural log of 9 minus x, whoops, is going to be n equals 0 to infinity of n equals 0 to infinity. This guy, that's my wife just arrived from the college. So if you can hear in the background. We got this. And this is the power series for the natural log of 9 minus x. But there are some style points to it. Don't we want an x to the n here if we can make it happen? Right, x to the n plus 1 is going to become x to the n. So I'm saying to myself, what do I need to do? And the answer is, I need to subtract 1, right? 1 from everything that's an n. So 1 away from that. The number -1 doesn't take part in this. If you take 1 away from n plus 1, you get n. And if you take 1 away from this power, you get 9 to the n. Looking good? Now, I made a mistake here, but I've caught it in time. When you added 1 here, right? Remember we added 1 here? Wasn't the effect on the sigma to take away 1? Right? What's going to be the effect on sigma, or on this guy, right? It used to be 0, if you subtract 1 from it. So what number will that actually start with?
1.
1. So if you add n to everybody, or if you add 1 to everybody, right, this goes down by 1. If you take 1 away from everybody, this goes up by 1, right? That's a little tweak at the end to make the sigma match the answer, right? If you didn't do that and you wrote out the answer in full, you would find out your terms were out of sync, right? You'd either have a term that was missing or you'd have a term that shouldn't be there, right? Everything else would be fine, but one of the terms would be wrong, either shouldn't be there or is missing, right? And that's what that little conversion. So it's just, if you take away 1, remember to add 1 to the sigma. If you take away 2, wouldn't you add 2? Right? If you take away 10, you'd add 10. But that's probably not going to happen. But if it did, that's what you would do. And in differentiation, very often what you do is you add 1 to all of these. And if you add 1, you work the other way around, right? You take away 1. So what have we got? I think I should do one more of the integrations, unless you feel comfortable with it. You want to see one more integration?
Yes.
Okay, let's pick it. Really doesn't matter who we do, they're all ugly. So we want to find that guy. And so I'm going to find the power series for this guy, and then I'm going to integrate it. Right? That's the strategy, right? Find the power series and then integrate it. In this case here, not sure you need this line, but I'm putting it in anyway. Can we pull out the t and then just focus on that? So in this case, we're looking at this one, which is that guy. So x is going to get replaced by t to the 7. So it's t times sigma n equals 0 to infinity t to the 7 to power of n. So that's basically x to the n. And I'll try and save a line of working here. Are we comfortable about 7n plus 1 more t? So I now have this guy. And we are being asked to find the power series for its integral. So if you want to integrate this guy, we're not actually going to integrate it. What we're going to do is tell you what the power series of the answer would be. So that means I'm going to integrate this guy. In this case, it's going to be add 1 to the power and divide by the new power. And then an arbitrary constant c. And that's fine. If it's possible, the rule is try and make it x to the n, t to the n, whatever the letter is. In this case here, I guess I could make that t to the 7n, but that's not really worth the effort. So actually that's the answer. If you're not going to change it in any way, you don't need to change anything, right? You're finished. So that one actually finished a lot quicker than I thought it was going to be. If I had wanted to change this to say t to the 7, wouldn't I take away 2 from this guy, 2 from this guy? And what would I do over here to compensate? If you take away 2 and you take away 2, what would I do to the n equals 0?
Add 2.
It'd add 2. So for those who want to know it, and you don't need to know this because web assigning, I don't think we need to know it either. That's what it would look like. I guess it is slightly prettier, would you agree? It's a little bit nicer looking, but it's still got a t to the 7, and I should say 7n. It's still got a t to the 7n in it, so it's not, a perfect x to the n kind of look to it, but it's pretty good. Any questions about that one? Then? We feel good about that one. Actually,
Yeah,
a lot. Yes.
just a quick question. You can only add or subtract from the ends. Can you not divide to get n by itself?
No, I wish. No, algebraically, it's not. There isn't a technique to do that
Okay.
correctly. So
Right,
you
thank you.
cannot. There's nothing you can do to make that t to the n, right? I guess you could stick a seventh root around it, but that doesn't work because you can't do seventh roots of adds, so you wouldn't be able to bring it inside. So no, there's nothing you could do to it to make it any better than it is. Now, the next thing is a big list of standard power series. These are the most common. I may have missed one or two, but I got most of them. Yeah. Remember x to the n, my favorite. That is by far my favorite power series, right? That's what e to the x looks like, power series. This is what the sine function looks like. And this is what the cosine function looks like. This is what the inverse tan function looks like. This is what the natural log of 1 plus x. Now you might think, why is it 1 plus x and not the natural log of x? Well, you have a problem at x equals 0, don't you, if you try and do that? Because the vertical asymptote. So this is essentially just shifted it one off. There's our two bread and butter ones that we've used a lot. And did I get them the right? I did, good. I got them the right way around for the change. Now, what you can do for many questions is you can use these guys as if they are given facts, like I'll just assume they're true. Because in a way, didn't we assume that these were true? Although I sort of approved it, right? Can we just assume for the time being that these are also true and we could prove them if you had time, right? So if you get one of these guys, you can also use it to generate other power series. I would like to know what e to the power of x squared is. And all I would do is think substitution. If e to the, let's bring this down a little touch. If e to the x is this guy, and I wanted to know the power series of e to the x squared, what transformation would I use? Well, in other words, what would I replace the x here with to generate the guy over there? Think substitution. What would you replace the x with? This x here.
Is that x squared, right?
Yeah. I mean, isn't that very similar to what you did with the 1 minus x squared and the 1 plus x squared, right? You use them as your building block and then you use the substitution. Now, to make this one look pretty, all I'm going to do is replace, well, express that in that way. And suppose I wanted to know the sine of 2x. Well, I know the power series for sine x, it's this ugly guy. And so if I want to know the sine of 2x, don't I just replace this x here by 2x? So this x with 2x. So it's going to be sigma n equals 0 to infinity, negative 1 to the n, 2x to the power of 2n plus 1, all over 2n plus 1 factorial. And then just basically make it pretty stale points. So negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 1, all over 2n plus 1 factorial. And the good news about these questions is don't even bother about trying to make them x to the n's because they're not going to be, right? So you can just leave them. They're as good as they want. I would like to know the power series for the cosine of the square root of x. Right. Here's my building block. That's the power series for cosine x. What's the substitution going to be now? What will I replace this x by?
The square root will replace the x in the base form.
Okay. Are you comfortable with the square root of x instead of an x? Right? Where there used to be an x, there is now a square root. And I'm going to make that pretty. The square root of x raised to the power of 2n is a bit weird looking, but it can be made nicer. So I'll do it over here. If I call the square root of x, x to the half power, then don't you multiply these together and whoa, don't you get a really nice answer? X to the half times 2n. Came out really nice. Any questions so far? If you know these guys, with a suitable choice of substitution, can't you also get power series for combinations or variations on these functions? So how about this as an example? I want to find a power series for the inverse tan of x over x. Well, the inverse tan of x over x is going to be called that guy. And I don't have any transformations. I'm just going to write this guy straight out. Right, so that's straightforward, writing down what you see. Okay, all you need to do now is get everybody inside a single sigma and you are done. Well, there's nothing on the bottom, there's nothing going to affect that. This 1 over x is going to come inside here, right? 1 over x is going to join up with this guy. What is the net power of x that you get when you take this fella and multiply it by that fella?
Well, +1 and -1, that would leave x to the 2n.
That's kind of cool, isn't it? You see that by only using these guys as building blocks, can't we get the power series of lots of other functions as long as they are in some way connected to these guys, right? How about this one? Where should we go? Let's do x squared, the natural log of 1 plus x. That guy is just a straight copy. Now, all I need to do is multiply by x squared. Oh, if you bring it inside, it just joins this guy. And technically speaking, I could make that x to the n, but we're not going to bother. I'm not going to do this next example, except talk through how I could do it if I wanted to. Can I get the power series for x squared e to the 2x? So when I find the power series of e to the 2x, by using that guy as my building block and replacing this x here with 2x, right? Imagine me doing that. Now, once I did that, wouldn't I just multiply everything inside by x squared, right? It's probably a 2-liner, you imagine? So we have a pretty resilient method for increasing the number of functions that we can get power series for. One of the biggest problems with power series, however, is that it's very difficult actually to create a full power series like this. If you just make life hard, you know, if somebody says, what's the power series of that guy? Well, I can find the power series of e to the x, I can find the power series of sine x, but wouldn't that mean I would have to somehow multiply this series with that series? And you see how that just is infinitely large, and won't all the terms be made up of different amounts of terms, right? There are only so many x cubes, but there are thousands of ways you get x to the 2 million, right? And so there's not a single one sigma. So that's one of the biggest drawbacks of power series, is that many functions cannot be written as power series, right? It's just too difficult to do, right? Maybe one day they'll invent a super computer that can just, you know, you bang in the thing you want and it'll do all the like 2 trillion calculations that you need to get the answer, and then it'll pop out a sigma for you and you can be suitably amazed when it does it. But until that day, we basically avoid trying to find power series for things we know that are not going to be doable, right? Physically doable at least. But there is a way around the problem, and that's true about most power series. Isn't most of the answer in the first 3, 4, 5 terms? So as long as you're choosing a value of x that's pretty close to 0, because these are all centered at 0. We'll show you Taylor series, how you can do one centered at another one, but these are all centered at 0. And you can do pretty precise calculations by only doing the first few terms. I'm not going to do that guy because that guy would probably be quite painful to do, but I'm going to do a very simple fella. Here is sine x, and sine x, as you can see, is n equals 0 to infinity, -1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. And I'm going to just write down a few of its terms. If you plug n equals 0, you get -1 to the 0, x to the 1 over 1 factorial. If you plug in x equals 2, you get -1, sorry, 1, x to the 2, that's x cubed, over 3 factorial. And then if you plug in the next one, you get -1 squared, x to the 5, all over 5 factorial. And let's make it pretty. -1 to the 0 is 1. 1 factorial is 1, so that basically gets you x. This gets you negative x cubed over 3 factorial, which is 6. And this one gets you plus x to the 5, and 5 factorials, I think it's 240, but let's just check. 5 times 4 times 3 times 2 times 1.
120.
I'm glad I checked, it's 120. Now, this is not the entire power series. Isn't this actually just the first 3 terms, right? 1, 2, 3. Just the first 3 terms. So technically speaking, I shouldn't be putting in equals here. Shouldn't I be putting the OC wavy line equal symbol, which means is approximately equal to, right? So it's not a perfect match, but it should be close. And so we're going to put it to a test. I would like to know, and it's in radians, what the sine of 0.1234567 is. Well, I can hopefully get that in my calculator, so make sure I'm in radians before I do anything. And I'm glad I checked, because I wasn't. And I'm going to do the sine of 0.1234567. And the answer I get is 0.123143326.9. And I'm pretty sure that's good to, what's that, 2, 4, 6, 7, 8. That's good to about 9 decimal places. Well, what does this look like as an approximation? So I'm now going to find what that comes to when I use 0.1234567. So that might take me a little while to type, and so keep with me if I screw up. So 0.1234567. Take away 0.1234567 cubed divided by, okay, I think I can get away with divided by 6. If this doesn't work, I'm going to have to go back and stick some more brackets around things. And then I'm going to add 0.1234567 times 7 to the power of 5 divided by 120. Okay, I'm about to hit enter. How impressed do you need to be that only 3 terms of that power series? Would you be impressed if it was good to 3 decimal places? Would you want 5? Would you be impressed if it was good to 5?
9.
Oh, you want 9? I'm not using you. You're definitely not an engineer. Here it goes. 0.123143326.9. Come on. 9 decimal places. I wasn't expecting that either. Do you know that if you want to find the sine of a function, don't you need to remember just that polynomial? Because won't the answer be, at least in this case, won't it be pretty close to being perfect? Actually, engineers only use a couple of decimal places, so they're happy anyway, right? In fact, if you were an engineer, wouldn't you probably just use that? Because you're really lazy. Well, have I convinced you that power series are actually quite useful for computing things? Now, if you think about it, how does a calculator find the sine of x? I bet you they have just stored that guy. You see how it can work? And then they have a little thing like if you travel too far away from 0, right, the answer gets worse. Do you notice when we drew it, it was great to round 0, but then it kind of drifted a little bit apart, right? But there's ways to fix that. You can put in a program where you only do the answer in, say 0 to pi, right? And then if somebody goes further than that, don't you just subtract a whole load of 2 pi's from it? So you've got an answer that's in your range, 0 to 2 pi, I should say, right? And you can do it that way. So there are ways to do it for almost any value. I am impressed, as you know, with power series. Are you impressed by how accurate they can be? Then we can move on. Is there anything that is left in that section that we've just done, which is section 11.9? Is there anything you want me to go over, or can we stick a fork in it and call it done? Okay, I am ready to move on then. Take me a few minutes to get the next one ready, put the heading in. And there we go. we're going to look at Taylor and Maclaurin series. These are just power series. They're called Taylor or Maclaurin, depending on whether the power series is centered at 0, in which case it's called a Maclaurin series. And if it's centered at some other value, like at 1 or 2, then it's called a Taylor series, right? And power series are either centered at 0 or they're not, right? So every power series is a Taylor or a Maclaurin series, right? So it's just a new name. In fact, the book's pretty inconsistent. What do I mean by that? If they say to you, you have a Taylor series centered at A equals 4, that's okay. If they say you have a Taylor series centered at A equals 0, and they say you have a Maclaurin series, they're actually the same thing. Isn't a Maclaurin series just a Taylor series centered at 0? What this is going to do, or at least what we're going to try and do, is create some of these power series that I told you were magic. And Maclaurin and Taylor came up with a way to do it. And they deserve a lot of praise in my book for figuring out how to do this. Right? So, first one I'm going to do is going to be for e to the x. And we're going to do Maclaurin series. Which are actually the most common one. So Maclaurin series are Taylor series centered at 0. So here is the formula using Maclaurin's method. The power series of this function, or any function f of x centered at 0, it's this guy, x to the power of n over n factorial, where this guy means the nth derivative evaluated at 0. What that tells us is that every function in the world, all the information you need to know about it is stored in its derivatives at 0. So if you can find all the derivatives of a function, right, at 0, and find a general way of writing them, you can create a power series. Unfortunately, only some functions have a nice pattern in their derivatives. Something you can actually say, the 10th derivative at 0 is this, right? A kind of general version, the nth derivative at this. If you can do that, you can create a power series, but it is possible. So what I'm going to do is start off with my function. And then we are going to find its various derivatives. Well, another reason why I like e to the x is that its derivative is always e to the x. So you write down the first 3 or 4 derivatives. And then you go dot, 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 and you try and find that guy. Now, on this side, we find the value of the function at 0, which is e to the 0. which is 1. And then the first derivative at 0 is 1. The second derivative at 0 is 1. The third derivative of 0 is 1. The fourth derivative at 0 is 1. This is a very nice pattern. Would you agree that I don't actually need to know this guy? Would it surprise you that the nth derivative at 0 is also going to be worth 1? So your goal is to find that guy. What is the nth derivative of your function at 0? In this case, it's very trivial. It's always the number 1, which means I can then go here and do sigma n equals 0 to infinity. The nth derivative at 0 is 1, x to the n over n factorial. And then you just tidy it up a little bit. There's your power series, so rate is x. Maclaurin series to be specific. Right, well, that was a baby one, right? Just to get us into it, right? There wasn't an awful lot of patterns here, right? So let's try, I need a new page. Let's try a function like number 1. And it's going to be 3x e to the x, okay? And here I'm going to do the value of this function at 0, which happens to be 0. And I'm doing the first derivative. And I'm probably going to have to do some working on the side, which is pretty common. If you want to differentiate that guy, you're going to have to use a product rule, agreed? And f dash g plus f of g dashed. So you're going to get 3 times e to the x plus 3x e to the x. And that's going to be 3 e to the x, 1 plus x. Okay. So that's 3 e to the x, 1 plus x. Now the first derivative at 0 is 3 times e to the 0 times 1. So it's just basically 3. Now I'm going to find the second derivative, which means I have to differentiate this. So there's my f, there's my g, and I'll have to do yet another product rule. And if you differentiate that, you get this guy. You leave this guy alone, you get that. You leave this guy alone, you get that. And you differentiate this guy, you get 1. And if you pull out the common factor, which is basically this guy, you get 2 plus x. So the second derivative is 3 lots of e to the x, 2 plus x. And the second derivative at 0 ends up being 3 times 1 times 2. And no, don't write this guy. Don't write this guy as 6. It's not helpful. Leave it as the calculation that you would get the 6 from, right? And I've just put them in order because I like things in order. And then you do it all over again. Can I just tell you that I know what the next answer is going to be because I can see a pattern? Right?
3ex. And is that going to be in parentheses of 3 plus x?
Yes. And if you don't believe us, check, but it works. So the third derivative at 0 ends up being 3 times 1 times 4. And I guess that's it. I'm going to call it 3 times 4 times 1 because I want to. Someone else this time. What would the fourth derivative be?
Would it be 3 e to the x and then parentheses 4 plus x?
Great. And so the fourth derivative at 0 would be 3 times 1. Oh, it's 0. Nobody caught that. That's a 3. Now it's 4. So that's going to be 3 times 4 times 1. Now the killer one. Based on the patterns at least 2 of you have seen, we now want to find what the nth derivative would be. So everybody has a 3 in it. Everybody has an e to the x in it. And then there's going to be a bracket. And everybody has a plus 1x. So basically, don't we need to figure out what should go here? And we've got the
N?
answer. And third
That's
derivative
right.
gets you 3, yeah? Third derivative, that's a 3. When it's the fourth derivative, that's a 4. If you don't trust me, do the fifth and sixth and seventh that you're comfortable. The nth derivative has an n there. Does that make sense? We're looking at a pattern. The third derivative, you get this with a 3 there. The fourth derivative, you get the same this, but with a 4 there. Won't the nth derivative get you this, but with an n there? And so all I need to do now is find out who this guy is, and we are ready to do a power series. Well, he's going to be 3 times e to the 0 plus n. And that ends up being 3 times n. Agreed? 3 times 1 times n, right? 3 times e to the 0, n plus 0, right? Which is just n. So power series is sigma n equals 0 to the infinity, the nth derivative at 0, x to the n over n factorial. And we have just found out that that guy was just 3n. There's your power series for 3x e to the x, if you wanted to do it from scratch. I don't think I'm too worried about this if you didn't see it, but I can make this a little bit prettier. That is a single n, not an n factorial, just a single n, but it will cancel out something on the bottom. What's going to be left on the bottom?
The rest of the factorial, right?
I think that's what I heard, n minus 1 factorial. You agree? You just kill off one term and you've left with most of the factorial untouched. Now, if you had to do it this way every single time, can you imagine that the questions would be horrendously big, right? And some people find it quite difficult to detect a pattern. So what are the kinds of questions that you get to do? Well, sometimes you get to find what's called a Taylor polynomial. So we never call them Maclaurin polynomials, even although they may be centered at 0. So if you wanted to do, for instance, by the way, the Taylor polynomials are called that, right? If you wanted to do T3 of x, you would be doing n equals 0 to 3. You would be essentially calculating up to x cubed. Now, since I want to do this function and I've got all the numbers I want, right? Let's pretend we didn't know the formula. It would go something like this. The nth, the 0 derivative at 0, x to the 0 over 0 factorial. the first derivative at 0, x over 1 factorial. The second derivative at 0, x squared over 2 factorial. And finally, the third derivative at 0, x cubed over 3 factorial. Now, I know that that guy is 3, so I'm putting him in. And 3x over 1 just gets you 3x. I know the next one is 6, so that guy there is going to be 6x squared over 2 factorial, which is 2. And I know the next one is what, 9. So this is going to be 9x cubed over 3 factorial. This ugly character here is a real pain in the butt, but he does have a number, right? He does exist. I'm pretty sure I told you that 0 factorial is 1, and you're just going to trust me that it's 1, right? Because it always will be. And would you agree x to the 0 is also 1? Now this funny, the 0 derivative to 0 is actually just him. You haven't done any derivatives. That's what the 0 derivative means. So the original function. In this case, that happens to be 0. So that term disappears. And so what I'm left with is 3x squared, and that's 6. And 9 over 6 gets you 3/2. And there is your Taylor polynomial. You might not be able to generate a perfect formula, but would you agree that you should be able to at least find the first 3 or 4 terms of any function, no matter how ugly they are, right? You can find the first derivative, the second derivative at 0, the third at 0, you know, whatever you need. And you will be able to create a Taylor's polynomial for it. And just like, remember I did the sin x and how accurate it was, can you imagine that this polynomial would be pretty accurate at whatever function you've got, right? So even the ugliest function in the world, as long as you pick something close to 0, this polynomial will get you a value very close to the original. So I guess we should try it. The function that this guy represents is this guy. Let's do the value of the function at 0.123. That's pretty close to 0. So its exact value is that, right? So let's see what that looks like. So it's going to be 3 times 0.123 times e to the power of 0.123. And I'm looking at 0.4172963513, right? And as far as we can tell, to 9 decimal places, that is the answer to this expression at that point. Now I'm going to find the Taylor's T3 guy at 0.123. So that's going to be 3 lots of this guy plus 3 lots of this guy squared plus 3/2 times this guy cubed. And I'm not going to ask Christoph Germany, because Germany, he has too high a wall to jump. So Caitlin's a much nicer student, right? Caitlin, how many decimal places will you be impressed by in this question?
Well, if it's anything like the last problem, I have a
No,
feeling
no,
it's
no,
gonna be a lot.
don't let Jeremy pollute you. If it was 4
Um,
decimal places, would you be quite happy if you were
No,
an
yeah.
engineer?
Yeah, 4 is good.
4 is good. So there's our little, let's see what we get. So it should be 3 times the number, so 3 times 0.123 plus 3 times that guy squared plus 3/2, which is 1.5, this guy cubed. And the answer that I got was 0.41 7, 1, 7, and some stuff. But if I round that off, it worked, didn't it? We got 4 decimal places. Now, some power series are really, really good. You might find a T3 of X, and as long as you're pretty close to 0, you get 9 decimal places. Remember E to the X, right? 9 decimal places, really good. Other functions, you're lucky if you get it to 1 decimal place, because some power series are just not very efficient, right? They will eventually get to the number you want, but you might need 10 or 20 terms. Luckily, in today's world, couldn't you write a program to do a power series and then just evaluate it to 200 places, right? 200 different terms, right? You could figure, Mathematica, I'm sure, can do it. And that's how you would estimate or replace a function with its polynomial. You might not be do the whole power series, but couldn't you at least estimate it with a T3 or a T10, right? Yeah, this is probably going to be our last one. This is question 3. We are now going to do a Maclaurin series. That means we're going to have to do the full table now, right? The whole thing from start to finish, which means we need to find a formula for the nth derivative of this function at 0. So here is the function at 0, it happens to be 9. If you do the derivative of this guy, it's -2 times 9, 1 minus x to the power of -3 times -1, so it ends up being positive. So what you've got is 2 times 9 times 1 minus x to the -3. And so the first derivative at 0 is essentially 2 times 9 times 1. So I won't worry writing that down. When you're looking for patterns, never turn this into 18. Just leave it as the calculation that you would get. So you notice that's a 2 and that's a 9, right? Now, second derivative. Well, if you differentiate this guy, you multiply by -3, right? Reduce the power by 1, and then that negative turns everybody into plus. So it looks like the second derivative at 0 is 2 times 9 times 3. Now, to save time, I'm going to tell you what the third derivative at 0 is. It ends up being 2 times 9 times 4. So I'm not right here. Yeah, times 4. Fourth derivative at 0 ends up being 2 times 9, and there's a 3 and a 4 there, times 3 times 4 times 5. And if I do the fifth derivative at 0, it ends up being 2 times 9 times 3 times 4 times 5 times 6. Well, you just trust me that that's what you get. Now I'm going to do a little rearranging here. I'm going to call that 9 times 2 times 3 times 4. And this one I'm going to call 9 times 2 times 3 times 4 times 5. And this one I'm going to call it 9 times 2 times 3 times 4 times 5 times 6. Now the killer. If you can figure out who he is, you've finished the question. The fifth derivative gets you this. The fourth derivative gets you this. The third derivative gets you this. Now, you need to look a little bit more carefully, and I wish I'd give myself more room, but I'll do it underneath.
And factorial?
It is a factorial. This guy, for instance, is 9 times 4 factorial. Stick a 1 in the front. Won't a 1 not do any difference, right? 1 times 2 times 3 is the same as 2 times 3. This guy is 9 times 5 factorial. And this guy is 9 times 6 factorial. Now, you did say a factorial, which was correct, Jeremy, but not the right one. I want to have another look at what is the formula for the nth derivative. And now you have to look at the 5th derivative gives me this. The 4th derivative gives me that. The 3rd derivative gets me that.
So n
What would
times
the nth derivative get me?
9 times the n plus 1 factorial.
Are you comfortable how we got that n plus 1 factorial guy? Even though I cut some corners to speed up because we're running short of time. Are you comfortable with the pattern that generates factorials? Right, 2 times 3 times 4 times 5. You ever see things like number times the next times the next times the next? Think factorials, because it's probably going to be that, right? And that is 6 factorial. If you really need to, can I stick a 1 in the front? Does that make you feel better, right? Can you see the factorial a little bit clearer? Then we should be able to find the power series, the Maclaurin series in this case. N equals 0 to infinity. The nth derivative at 0, x to the n over n factorial. That looks good. So it's going to be sigma n equals 0 to infinity. This guy, x to the n, still over n factorial, right? I mean, these two guys are always there, right? They're always there, right? They're part of the formula. Now, style points.
Nine x plus 1 to x n.
Are you comfortable how the n plus 1 factorial on the top cancels out with the n factorial on the bottom, and there's a single n plus 1 left on the top? Are you comfortable about that algebra? Do you want to see it written down a little bit longer? So this becomes that. I'm looking for feedback. Are you okay with that? It makes sense. I don't need to show you. Okay. And we now know the exact power series for that guy. Here's this thing. Oops. Here's this thing. And if I wanted to estimate it, I could find T3 of X, couldn't I? Or T2 of X, whatever I felt like, and use that to estimate the answer. I think for a function like this, you could probably just do it the normal way, right? It's not a difficult function to evaluate. Any questions? Been quite heavy duty stuff today. I get time for one more. Do you want me to do it? One more function?
Yes, please.
Okay. Let's do one of the guys that I told you what he was equal to. I'll just pick it and then we can go looking. Let's go for the power series, right? The Maclaurin series for that function. Right. So the value of the function at 0 is the natural log of 1, which is just 0. Okay. If you differentiate this guy, you get 1 over 1 plus x, and the first derivative at 0 is 1. If you find the second derivative, you probably should call this guy that fella, right? Just to make it easier to differentiate. So the second derivative is -1 times 1 plus x to -2, and the second derivative at 0 ends up being -1 times 1, so it's -1 times 1. Now if you find the next derivative, the third, you're going to need these two guys, so it's going to be positive. It's going to be 1 times 2 that guy. And the third derivative at 0 ends up being 1 times 2 and positive. If I do the fourth derivative, it ends up being negative 1 times 2 times 3, 1 plus x to the -4. And so the fourth derivative at 0 ends up being negative 1 times 2 times 3 times 1. But I'm not going to put the times 1 in, it doesn't need to be there. Anybody want to tell me what the fifth derivative at 0 is? Just looking at the pattern you can see here.
That let's see, 1, 2, 3, 1 times 2 times 3 times 4
Yes. And will it be
Yeah.
positive or negative?
without the negative sign.
So again, there,
Positive.
positive, agreed. Somebody else then? Tell me what the sixth derivative would be.
-1 times 2 times 3 times 4 times 5.
Right. Now, if we want to condense that, wouldn't this be better to be called 4 factorial? And wouldn't this be better to be called -5 factorial? This guy would be easier to call -3 factorial, +2 factorial, and -1 factorial, and +0 factorial, I guess, right? Now, if you can see this pattern, you are almost home and dry. It's all about pattern recognition. Now, let's not worry about the plus minus. I'll sort that out in a minute. But can you tell me what kind of factorial do you get with an nth derivative based on the answers you got to all of these derivatives?
I would suggest around n-1 factorial.
So the fifth one gets you 4, right? And the sixth one gets you 5. Would you agree? n-1 for the nth. Now, it's not uncommon when you do power series to get this plus minus thing going on, right? And when you've got a plus minus thing, there's one of two possible answers. It's going to be that guy or it's going to be the guy underneath, right? And it doesn't depend on which one they start with. They start with a plus or a negative, right? All that carry on, right? So one of the simplest ways is pick one and see if it works. If it works, use it. If it doesn't work, it's the other one. Okay, so I'm going to pick, for no particular reason, that the fifth derivative, that one there, should be positive, right? Now, if you put -1 to the power of 5 in here and some stuff, and you put -1 to the power of 6 in here, do you see this is the one that gives you the positive answer? Which means this is the one I should be using. Now, it's not very scientific, isn't it, like guess and check? But you know there are only two answers, so it's not too difficult to guess and check, right? It's either the n or the n+1, and you're good to go. So we put this package together then, and so the original function, its complete Maclaurin series is n equals 0 to infinity. The nth derivative at 0, x to the n over n factorial. So it's going to be n equals 0 to infinity. The nth derivative was -1 to the n plus 1, n-1 factorial, x to the n, all over n factorial. Okay, let's make it pretty, and we are done. Okay, don't do anything with that guy, don't do anything with that guy. If this fella here interacts with that guy, there is a lot of cancelling going on. What's left? And is it in the top or is it in the bottom?
And on the bottom.
And in the bottom. Are we all comfortable with that? So I'm now going to find my piece of paper and prove to you, then show you that's what I wrote down. Of course, knowing me, I may have written the wrong one then. Oh, okay. This guy has an n-1 on it. and this guy has an n plus 1. Do you see that? The good news, doesn't that make no difference? They behave exactly the same. So I could have just made that a +1 to match up with that one. So we have now got a mechanism for finding Maclaurin series. It's quite cumbersome, right? You have to find the first, second, third, fourth, fifth derivative at 0, figure out some pattern so that you can get the nth derivative at 0. Once you've got the nth derivative at 0, put in what your pattern says it is. Do some cancelling if there is any, and you've now got your final answer.
But
And-
you do have to do the sigma to n equals 0 and to an n equals 1.
In this guy here, should be 0. I don't see why. Did I put 1? Oh, I put 1. Let me do a check. If you put in 0, you get. Ooh, there's a good reason why that is 1, which is what's over here. Why is 0 a bad idea for this power series? Because it was caught over here. Why shouldn't you or can't you use n equals 0 in this power series?
We'll make everything 0.
And you don't want 0 on the bottom, especially, don't you? So that was just a little tweak. Well caught, I never saw it. Last name, bye-bye. See you tomorrow, Melbourne? Yeah, I will. I'll see you tomorrow. And we are getting close to finishing these. I know it's a heck of a long chapter. It's by far the longest chapter that you're going to do. If it makes you feel better, the next chapter, chapter 10, can be done in inside a week. That's how quick it's going to be, right? So I'll hang about for questions and bye-bye for now.
Have a good one.
I will try, you too.
So I have a question about the last thing we did.
This
So
guy?
yeah, so what
Okay.
happened to the 1 plus x to the n?
1 plus x to the n. Oh, this guy? Oh, why is this guy not a 1 plus x? Is that what you're asking?
Let me see, the derivative to the nth power, wouldn't that be -1 to the n plus 1 times n minus 1 factorial times 1 plus x to the -n?
Okay, but what happens when you put x as 0? Doesn't that just become 1 to the power of -n, which is just 1, so it
Oh,
disappears
okay.
inside the calculation?
Okay.
Because when we do this, we evaluate the derivative at a specific number 0.
Oh,
In that case, that 1 plus x bit you're talking about ends up being 1, and times 1 doesn't change anything, so we don't write.
okay. Awesome. Thank you.